Greetings, students, from my journey to the wilds of Iowa and Nebraska. Welcome, welcome, come with me. You've made it this far. You're ready to conquer the mythical beast that is stoichiometry. Whether you believe in it or not, it's true, it's here. Let's vanquish the beast. Let's talk about it first. What are we going to do in this unit? We're going to define stoichiometry, describe its importance. We're going to relate stoichiometry to balanced chemical equations, which you just did. And you're going to identify and solve different types of stoichiometry problems. We're going to start out going mole to mole. That's the easy stuff. Then we're going to do our mass, volume, or particles to mole. And then we're going to do some limiting reactions, reactants, and we'll talk about it. And then finally percent yield. So I'm excited. I hope you are too. Let's go. So here's the thinker. You want to make a cheese sandwich. Cheese sandwiches aren't particularly complicated. There is one piece of cheese and 2 slices of bread. Well, if you had 7 slices of bread, how many sandwiches could you make with that? Well, you need 2 per sandwich. So that means you can make 6 sandwiches, and you'd have 1 left over. 3 sandwiches, because you're only going to have 1 left over, because you need 2 each. Caught myself there. How about 6 pieces of cheese? Well, how many sandwiches can you make? Well, you can make 6, presumably. But if you need both of these parts, then actually you could only make 3 sandwiches. You'd have 1 slice of bread left over, and you'd have 6 slices of cheese left over, but you could only make 3 sandwiches. And that's really what we're talking about. We're talking stoichiometry. So let's talk about information given by balance equations. Really, why would we bother balancing the equations? We did it. We got good at it. Why do we care? So balance equations are really just recipes that require properly proportioned ingredients. That's all they are. They give us proper proportions for chemicals. So if we have 2Na, 2 plus 2H2O yields 2 sodium hydroxide and hydrogen, this is properly balanced, and this gives us the proportions. If you know you need so many chocolate chips for cookies, you need that certain amount. If you put a whole bunch of chocolate chips, that's probably it might ruin your whole recipe. And really, balanced equations are just recipes for chemical reactions. What this means really is 2 sodium atoms plus 2 water molecules yields 2 formula units of sodium hydroxide and 1 molecule of hydrogen. But what it also means, because we're not going to measure some atoms or measure some molecules or measure formula units easily, we interpret coefficients as moles. Look at our friend moles that came back here. Guys, you learned it all for a reason. So, what this really means is 2 moles of sodium plus 2 moles of water molecules yields 2 moles of sodium hydroxide and 1 mole of hydrogen. That's what we're dealing with here. Because we can measure moles and we can see moles. These are quantities that we can actually work with, since we need so many darn atoms or molecules. Stoichiometry. It is a branch of chemistry. It's from the Greek stoichion, which means to measure elements. It's all about measuring. And it deals with quantities of substances in chemical reactions. So, here's some things to remember. 1 mole equals molar or molecular mass of grams. 1 mole is 6.02 times 10 to the 23rd particles. And 1 mole is 22.4 liters of a gas. So just wanted to point out these people here, these fancy people, are Joseph Black and Rutherford, who are integral in really pioneering this field. So let's do an example problem, because I always think example problems are the best way to go about it. So if we wanted to make commercial ammonia, it's used in cleaning, things like that. How do you do that? Well, you take nitrogen, you take hydrogen, and you get ammonia. This is the Haber process. But we could ask the question, how many moles of hydrogen are necessary to make 312 moles of ammonia, assuming excess nitrogen? And what that means is that you have all the nitrogen that you could ever need. Excess nitrogen. You don't have to worry about it. So we use dimensional analysis. We have 312 moles of ammonia. We know that's our given in this problem, even though it's the end goal. It's still our given, our number in our unit. And so we're going to multiply it by the ratio between the two. We have moles of ammonia here, so we need moles of ammonia down here. You can see that. But notice it's 2 moles of ammonia right from here. And we have 3 moles of hydrogen gas right here. The hydrogen gas comes right, or the 3 comes right down here, and this is our ratio. 3 moles of hydrogen to 2 moles of ammonia. And so that cancels, that cancels. We're now in the right units, moles of hydrogen. And that equals 468 moles of hydrogen. Just multiplying across, dividing by 2. 312 times 3 divided by 2. 468 moles of hydrogen. And again, moles in, or sig figs in equals sig figs out. Let's do another problem. How much oxygen is formed by the following reaction if 1.3 moles of H2O2 decomposes completely? So H2O2, hydrogen peroxide, we know breaks down into water and oxygen. And we're not forcing you to do the balancing right here. We're giving you this gift of pre-balanced equations. You're welcome. So we know, though, that we have 2 moles of hydrogen peroxide and 2 moles of water, or yields 2 moles of water and 1 mole of oxygen. So how much is going to be produced? Well, again, what's our given? Well, we know it's going to be 1.3 moles of H2O2. It's important to write down the whole thing. 1.34 moles H2O2. I'm going to catch people just writing moles, and then they're going to mess it up later. Because you want the whole unit to go out. Moles of H2O2 and moles of H2O2. Again, we have this ratio here. So we know we need 2 here. And from our equation, we get 1 here. So we have 1 mole of oxygen here. It's super simple. 1.34 moles H2O2 times 1 divided by 2. These cancel out. And we get 0.670 moles of O2. And it's 3 sig figs in, 3 sig figs out. Remember, because this is after a decimal, this is definitely a significant digit. It counts. Now we could ask how much water is formed. Again, 1.34 moles H2O2. We know the bottom, the denominator, definitely going to be 2 moles H2O2 because we already grabbed it from up here. But how many moles of water? 2 moles of water. Again, the 2 comes from here. This 2 comes from there. Our units cancel. Moles of H2O2, moles of H2O2. And we get 1.3 moles of H2O. And we could have probably figured that out when we know 2 over 2. But for every mole of hydrogen peroxide you put in, you get a mole of water from our equation. So I'd like you to try this problem. Show your work. I want you to balance the following equation and then answer the questions. So you're going to write out iron 3 oxide plus aluminum yields iron plus aluminum oxide. You could absolutely do this. So after you've balanced that out, how many moles of aluminum are needed to completely react with 3.30 moles of iron 3 oxide? And how many moles of iron are formed from 3.30 moles of iron 3 oxide with excess aluminum? These are your questions. So good luck. I look forward to seeing your answers and seeing how you guys can do. Remember to use dimensional analysis. Remember to cancel out, write down all the units because you're going to cancel out all the units, and you can absolutely do this. Good luck, and I hope that was helpful.